From beneath the oceans to the peaks of mountains, humanity is reshaping the planet on a scale never seen before. Massive tunnels are built under seas, connecting cities separated by kilometers of water. Dams rise across powerful rivers, holding back trillions of kilograms of water while generating electricity for entire nations. Bridges stretch across vast distances, carrying millions of vehicles every year. Roads, railways, pipelines, and foundations are constructed with millimeter precision, often in environments once thought impossible to control. These are not ordinary construction projects. They are mega projects, complex systems where engineering, geology, technology, and human ambition intersect. Each structure begins as an idea, but turning that idea into reality requires overcoming natural forces such as gravity, water pressure, earthquakes, wind, and erosion. A single miscalculation can lead to catastrophic failure, yet success can transform economies, improve living standards, and redefine how societies move, communicate, and produce energy. Behind every tunnel, dam, or bridge lies years of planning, advanced machinery, and thousands of skilled workers operating under extreme conditions. These projects are designed not just to function today, but to endure for decades under constant stress. As the demand for energy, transportation, and infrastructure continues to grow, engineers are pushed to innovate faster and build bigger than ever before. This is the world of modern mega construction, where precision is critical, risks are enormous, and the margin for error is almost zero. In this documentary, we explore how these extraordinary structures are built, the technologies that make them possible, and the challenges engineers face when constructing at the limits of what humans can achieve. Modern mega construction projects represent the highest level of coordination between engineering, technology, and large-scale logistics. These projects are planned years before physical construction begins, often requiring extensive geological surveys, environmental assessments, and simulation modeling. Engineers must first understand the natural conditions of the site, including soil composition, seismic activity, water movement, and long-term climate behavior. Only after these factors are analyzed can construction methods be selected that ensure safety, durability, and efficiency. One of the most technically demanding examples of modern construction is underwater tunneling. These tunnels are designed to function under immense external water pressure while remaining completely sealed and structurally stable. Construction typically starts with seabed preparation, where the ground is leveled and reinforced. Prefabricated tunnel segments are manufactured in controlled environments to ensure consistent quality. These segments are then transported to the construction site and lowered into position using specialized floating cranes. Alignment is achieved using advanced positioning systems, often supported by satellite guidance and laser measurements. Once in place, the segments are connected using high-strength seals that prevent water intrusion. Additional protective coatings are applied to resist corrosion caused by saltwater exposure. After structural assembly, internal systems such as ventilation, lighting, fire protection, and emergency exits are installed to meet safety regulations. Underwater tunnels significantly reduce travel time, support trade, and provide reliable transportation routes that are unaffected by surface weather conditions. Large dams are another critical component of global infrastructure, designed to regulate water flow and generate renewable energy. The construction of a dam begins with diverting the natural river course, using temporary barriers and bypass channels. This process allows engineers to access the riverbed in dry conditions. Excavation follows, removing unstable material until solid bedrock is reached. A reinforced foundation is then constructed to support the massive weight of the dam structure. Concrete placement is carried out in stages, with each section engineered to withstand immense hydrostatic pressure. Cooling systems are often embedded within the concrete to manage heat generated during curing. Once the main structure is complete, turbines and generators are installed to convert the kinetic energy of flowing water into electricity. Dams also incorporate spillways and drainage systems to control excess water during floods. In addition to energy production, dams support irrigation, urban water supply, and flood mitigation, making them essential for regional development. Bridge construction has evolved significantly with the advancement of materials and machinery. The process begins with deep foundation work, where piles are driven or drilled into stable ground layers beneath rivers or seabeds. These foundations transfer loads safely into the earth. Bridge piers are then constructed using reinforced concrete and steel frameworks designed to resist environmental forces such as wind, current, and seismic movement. Superstructure assembly follows, with beams, decks, and cables installed using large cranes and temporary supports. In cable-supported designs, tensioned cables distribute loads evenly, allowing bridges to span long distances without intermediate supports. Final construction stages include roadway surfacing, expansion joints, drainage systems, and safety features. Beyond their functional role, bridges often serve as key transport corridors that enable economic growth and regional connectivity. Railway infrastructure has also benefited from automation and precision engineering. Modern rail construction increasingly relies on mechanized systems capable of installing tracks with minimal human intervention. Automated machines lift rails, align them precisely on prepared track beds, and secure them using fastening systems controlled by sensors and computer guidance. These technologies ensure consistent alignment and reduce construction time while improving safety. Accurate rail placement is essential for high-speed and heavy-load rail systems, where even small deviations can affect performance and maintenance costs. River engineering projects focus on controlling water movement while maintaining long-term stability. Construction typically begins by isolating the work area through temporary diversion channels. Foundations are reinforced using concrete and steel structures designed to manage flow velocity and pressure. These systems regulate water levels, prevent erosion, and protect surrounding land. Continuous monitoring through sensors allows engineers to track structural behavior and water dynamics in real time, enabling rapid response to changing conditions. Road construction remains one of the most widespread forms of infrastructure development. It begins with site clearing and ground stabilization, followed by the placement of layered materials that form a durable base. Each layer is compacted to achieve the required strength. Asphalt is applied at controlled temperatures and finished using rollers to ensure a smooth and resilient surface. Markings, barriers, drainage systems, and signage are added to prepare the road for safe use. Modern construction techniques emphasize efficiency and environmental responsibility, reducing material waste and energy consumption. Coastal protection projects, such as seawalls and breakwaters, are designed to shield shorelines from wave action and erosion. These structures are built using large rock units or concrete elements placed strategically to absorb and disperse wave energy. Underwater surveys guide precise placement, ensuring stability even under extreme conditions. Such projects protect infrastructure, ecosystems, and communities located along vulnerable coastlines. Advances in building materials have led to faster and more sustainable construction methods. Lightweight concrete block systems allow for rapid assembly without traditional mortar, improving thermal insulation and reducing energy usage. These materials are engineered to resist fire and seismic forces while minimizing environmental impact. Retaining wall systems using interlocking precast blocks provide effective solutions for slope stabilization and landscaping. Their modular design allows quick installation and structural reliability with reduced labor requirements. Foundation systems using recycled materials further support sustainable construction by offering insulation, moisture resistance, and durability, while reducing resource consumption. Infrastructure also includes marine pipelines that transport oil and gas across underwater routes. These pipelines are installed following detailed seabed surveys that identify hazards and optimal paths. Pipes are welded and tested aboard specialized vessels, coated for corrosion protection, and carefully lowered to the seafloor. Controlled installation angles prevent structural damage during placement. Once connected to onshore facilities, these pipelines form critical links in global energy networks. Road tunnels play an essential role in modern transportation by allowing vehicles to pass through mountains, urban areas, and underwater environments. Tunnels reduce travel distances and avoid surface obstacles, improving efficiency and safety. Their design includes ventilation, lighting, monitoring, and emergency systems that ensure continuous operation under heavy traffic loads. Mega projects as a whole drive technological advancement and economic development. They create employment, stimulate innovation, and expand infrastructure capacity. At the same time, they require careful planning to manage environmental and social impacts. As global demand for energy, transportation, and resilient infrastructure continues to rise, mega construction projects will remain central to shaping how societies grow and function in the modern world.